Now that we've gotten really good at finding derivatives of functions using the definition, the limit as h goes to 0 of f of x plus h minus f of x all over h, we're going to look at a couple shortcuts to make life a little easier for us. First, I want to make a point of noting that there are many ways to write the derivative of f of x. One way we do it is we put a little prime after the f. We'll say f prime of x, and that just means the derivative of the function x. Another way we'll see it is we will say dy dx. That means the dy dx. That means the derivative of y with respect to x. Another way you might see derivative written is we take d dx of f of x. So the derivative with respect to x of the function. And then one that's used less often, but we still see it on occasion, is we'll see d sub x of the function f of x. Part of the problem with notating calculus is calculus was developed by two men in separate places at the same time, and so each of them published their own notation to mean things. And so there's a little bit of fuzziness between the two notations depending on whose book people bought first and whose philosophy they bought into first, and so it never really got standardized. So all four of these really mean the same thing. It means we're going to take the derivative of the function f of x. Now, we're going to look at a couple shortcuts we can use to help us with derivatives. Because this is a business calculus and not an engineering calculus class, we're not going to bother with deriving these formulas and proving they're true. So if you would really like to see why these are true, we can do that with the definition of a derivative. Feel free to ask me about them in class or catch me in my office and we can look at why they're true. But for now, I'm just going to tell you they're true, and we're going to try and use them to help us take derivatives much quicker than we've been doing them in the past. So rules of derivatives. We're going to look at 4 rules of derivatives, and for these rules, f of x and g of x are functions, and k is going to represent a constant, like the number 3. It's constantly 3. The number pi is constantly pi. So first rule is if f of x, if the function is equal to a constant, and we were to take the derivative of that constant, that's always going to be 0. So for example, if f of x equals 3, and we wanted the derivative of 3, f prime of x, the derivative of any constant number, is always going to be equal to 0. It doesn't matter what that number is. F of x could equal e. E is that Euler's constant. We use it in the natural log a lot, but it's still a constant. It's always equal to 2.18, so the derivative of e is 0. The derivative of any constant is always 0. That's our first rule of derivatives. The second rule of derivatives that we're going to use a lot is if f of x is equal to x to some exponent. And you may have started to notice this pattern from our lesson before, that if we want to take the derivative of x to some power, we put the exponent out front, and then the exponent's going to reduce by 1. So, for example, if y equals x to the fifth, dy dx, the derivative, is going to be equal to, and that should probably be blue to be consistent, dy dx, we can take the 5 and move it out front, and then drop the exponent by a single digit. So the derivative of x to the fifth is 5x to the fourth. And we can play with this with any type of exponent. For example, if we have y equals 1 over x to the fourth, it might not be as obvious just looking at it, but remember, x to the fourth in the denominator is like x to the negative fourth in the numerator. So if we want to take dy dx, the derivative, we move the exponent out front, negative 4x, and then we raise that to 1 less power. 1 less than negative 4 is negative 5. We can even do it with fractional exponents. Let's say we have y is equal to the cube root of x squared. Remember, radicals can be written as a fraction where the index is the denominator. So this is really x to the 2/3 power, which means the derivative, dy dx, is equal to, move the 2/3 out front, x to the 2/3 minus 1. 1 is 3/3. 2/3 minus 1 is negative 1/3. So x to the negative 1/3 power. So that is a nice little property that lets us take lots of derivatives really quickly by putting the exponent out front and taking 1 away from the exponent. Let's take a look at a third property. A third property is if f of x is equal to some constant times a function. It turns out that f prime of x, that constant doesn't change anything. It's still out front, and it's equal to the constant times the derivative. So, for example, if we have y equals 7x to the fifth, we've got a constant out front. Y prime is equal to 7 times the derivative of x to the fifth. Well, that's bring the exponent out front and then subtract 1 from it. Essentially, we're saying y prime, the derivative, is equal to 7 times 5, 35x to the fourth. Just multiply the constant times the derivative. So if we have, y equal to 7 over 3x to the sixth, get that x to the sixth out of the denominator. We're going to do 7/3 times x to the negative sixth. That way, we can use that nice exponent property. Y prime, the derivative, is equal to 7/3 times the derivative of x to the negative sixth, which is negative 6x, subtract 1, to the negative 7th. And we can simplify this. 6 over 3 is going to be negative 2, so we have y prime equals 7 times 2, negative 14, x to the negative 7th. That's our third property. A fourth property that we're going to use to help us with our derivatives is if f of x is equal to some function g of x, and we either add or subtract another function h of x, With adding or subtracting, we cannot do this with multiplying and dividing. Very important. We cannot do this with multiplying and dividing. But we can do it with adding and subtracting. F prime, the derivative, is equal to the derivative of the first part plus or minus the derivative of the second part. So, for example, if f of x is equal to some long polynomial, maybe 3x to the fifth minus 2x to the fourth plus 6x cubed plus 7x minus 2, we can take the derivative of this entire thing by just taking the derivatives of the pieces that are added together. Let's do another notation. We've already done f prime. Let's do the notation d sub x of f of x. The derivative with respect to x of f of x is 3 times the derivative of x to the fifth, which is 5x to the fourth, minus 2 times the derivative of x to the fourth, which is 4x cubed, plus 6 times x cubed is 3x squared, plus 7 times x to the first, which is 1, x to the 0, 1 minus 1 is 0, minus 2, but that's a constant. 2 is a constant. The derivative of minus 2 is 0. So cleaning it up, the derivative with respect to x of f of x, 3 times 5 is 15, x to the fourth, minus 2 times 4 is 8, x to the third, plus 6 times 3 is 18, x squared, plus 7 times 1 is 7, and remember x to the 0 is 1, minus 0 is nothing, and so we now have this derivative. Let's try another example. How about if f of x is equal to 7x squared plus 3 square root of x minus 7 over x squared. Remember, we have our exponent property that if we've got x to some power, it's really easy. Pull the power out front, subtract 1 from the power. So let's rewrite this function as all exponents. 7x to the second, that's good, plus 3x to the square root, remember, has a 2 in the index, so that's really 3x to the 1/2. Minus 7x to the, because it's coming out of the denominator, it's a negative exponent. By rewriting the problem like this, we've created a problem that's much easier to take the derivative of. We can say d dx of f of x is equal to 7 times the derivative of x squared is 2x to the first, plus 3 times the derivative of 1/2 x, or x to the 1/2, is bring the 1/2 out front, x to the negative 1/2, subtracting 1, minus 7 times, bring the exponent out front, negative 2, x to the negative 3. Then we just have to clean it up. d dx, the derivative of f of x with respect to x. 7 times 2 is 14x, plus 3/2, x to the negative 1/2, plus negative 7 times negative 2 is positive 14 x to the negative 3. And now we have our derivative. This strategy to rewrite problems that look complex, but rewrite them like we did in orange here in the center, rewrite them so that we have x to some power, is going to be very useful to us as we solve some more complex and involved derivatives. For example, if we have f of x equals 3x squared minus 2 square root of x plus 5, all divided by x. And we want the derivative of this. Well, one thing we should see is the square root is really x to the 1/2. So think about the square root as x to the 1/2. And then you see this entire fraction is divided by x. We can take this concept and distribute that divide by x onto each term. So f of x is equal to 3x squared divided by x minus 2x to the 1/2 divided by x plus 5 divided by x. And we can reduce these fractions. The first one, 2 minus 1, is 3x to the first, minus 2 times x to the, subtracting the exponents, 1/2 minus 1 is negative 1/2, plus 5x to the negative 1 to represent the fraction. Now that it is written as a polynomial, we can take the derivative. F prime of x is equal to 3 times. The derivative of x is just 1, because x to the 0 is nothing, minus 2 times, we put the negative 1/2 out front, and subtract 1. Negative 1/2 minus 1, or 2/2, is negative 3/2. So x to the negative 3/2 plus 5 times negative 1, x to the negative 2. Clean it up. F prime of x is equal to 3 plus, the 2's divide out, negative times a negative is a positive, 1x to the negative 3/2 minus 5x to the negative 2. We now have our derivative. We can use this idea to find all sorts of derivatives. Let's say f of x is equal to 3x minus 7 squared. Now granted, we can't do anything with 3x minus 7 squared. We don't have a property yet on how to handle this. But what we can do is rewrite the f of x by multiplying out the polynomial. When we do, we get 9x squared minus 42x plus 49. Now we can take the derivative of f of x. We have 9 times the derivative of x squared, which is 2x, minus 42 times the derivative of x, which is 1, plus 49. Whoa, no. Sorry. Plus the derivative of 49. 49 is a constant, so that's going to be 0. Clean it up. We've got the derivative of f of x is equal to 18x minus 42. So today we're talking about 4 techniques to help us find derivatives quicker than using the definition. As a quick review, the first property is the derivative of a constant is always equal to 0. Our second property, the derivative of a polynomial, something with an exponent, bring the exponent out front and then subtract 1 from the exponent. Our third property is if the function has a constant out front, we keep the constant out front and then multiply by the derivative of the function. Our fourth property is if they're adding and subtracting, we can take the derivative of each term individually. These are properties you're going to want to have memorized as quick as possible. You should be able to do these derivatives very quickly. 4 important properties. We're going to have about 10 by the time we're done with this unit. But let's, now that we can find derivatives quickly, let's talk about a place we can actually use derivatives in business with something called marginal analysis. A little bit of definitions to kind of set up what marginal analysis is talking about. When you see the word marginal, what we're talking about really is what is the rate of change in the problem. And remember, rate of change is just another way to say derivative. So when we see a marginal analysis, what we're really doing is we're calculating a bunch of derivatives. And often we will see marginal cost. You might see marginal revenue. You might see marginal profit. This is the cost, or the revenue, or the profit, depending on the context, of producing one more item. Is there going to be a big return if we just produce one more? Or is there going to be a big expense if we produce one more? And the idea here between marginal analysis is you'll have some type of graph, some type of model that represents your profits. And if x is down here, producing one more will be x plus 1. And so really the change is going to be the slope of the tangent line that goes, the slope of the secant line that goes through these 2 points. I'm trying to make it a little thicker, but I'm just making it messy. Now, in reality, at x, the derivative is the slope of the tangent line that just barely touches that point. But what I want to notice in my curvy line, whoops, what I want to notice with my curvy line, let me try again, is the tangent line is pretty darn close, especially in the area we're interested in. The tangent line and the secant line are very, very close to each other. In fact, we might even take a note of that. The tangent is very close to the secant with x plus 1. And as it turns out, a lot of the times it's a lot easier to work with the derivative, or the slope of the tangent line, than it is to work with the actual values. It's going to be a lot more work to calculate the value at x and the value at x plus 1 and calculate the difference. So we will use the tangent line to help us estimate the actual difference. And they're going to be pretty darn close to each other. For example, suppose the cost to produce a product is the cost, c of x, is equal to 2x squared plus 50x plus 250. We're going to find the marginal cost of the 5th item. In other words, if we have 5 items, what is it going to cost us to produce another item, to produce a 6th item? How much more is that going to be? Well, it's going to be a pain to plug 5 in to all the x's and find out what the answer is, and then plug 6 in to all the x's and find out what the answer is, and then subtract them. Calculus makes this much easier. we can take the derivative of the cost function. If we bring the exponent out front, we get 2 times 2, which is 4x to the first, plus 50 times the derivative of x, which is just 50. And the derivative of 250 is nothing. So this is the derivative of the cost function. We want to find the fifth item. Well, 4 times 5 plus 50 is equal to 70. It's going to cost about $70 to produce one more item, or to produce a sixth item. That gives us a really nice ballpark figure, and that was really quick and easy. I want to compare that to the actual numbers. The way we find the actual number is we have to figure out what C of 5 is, which is 2 times 5 squared plus 50 times 5 plus 250. And when we do all that, we get 550 using the calculator. Then we need to know what C of 6 is, so we know what the sixth item is. 2 times 6 squared plus 50 times 6 plus 250. Calculate that out, we get 622. And then we need to subtract those to find the marginal, or the change in the cost. So 622 minus 550, that's going to be $72. That, though, required a lot of work, a lot of calculation, and a lot of grinding. Notice the answer was really close, and when we're talking about producing millions of items and millions of dollars, a difference of $2 between the actual and the derivative's estimate is not really significant. And so this is why we usually prefer using the derivative and getting a close estimate, rather than going through all the work of calculating the actual numbers. Let's take a look at another example with marginal analysis. Revenue is calculated, if I can spell calculated, by the number of items that you sell times the price per item. So, for example, if you sell 3 items for $5, you've made $15. 3 times 5 is 15. That's pretty straightforward. Your book uses, for the number of items, it uses the variable Q, and for the price of the item, it uses the variable P. And as it turns out, price is often a function of the number sold. And that makes sense if you think about it. The higher the price, the fewer you'll sell. The lower the price, the more you sell. Yes, that oversimplifies economics a bit, but the principle is still there. Price is a function of the number sold. This number sold, this is called the demand function. For example, there might be a demand function like R of Q. I'm sorry, there's a revenue function. A revenue function, R of Q, is equal to the number times the price. But the price is a demand function based on the number sold. So, for example, we can find the marginal revenue when Q equals 10,000, 10,000 items, if the demand is P equals 50,000 minus Q over 25,000. Well, the revenue of Q is equal to Q times P. We're going to keep the Q for a minute. Q times P, which is 50,000 minus Q over 25,000. Let's distribute. That's really Q over 1. We're going to distribute the Q into the numerator so that R of Q is equal to 50,000 Q minus Q squared all over 25,000. Let's divide the 25,000 by both parts, splitting up into fractions. So we have R of cubed is equal to 50,000 over 25,000. 50 over 25 reduces to 2, Q, minus 1 over 25,000, Q squared. We can easily take the derivative of this. The derivative of 2Q is 2 minus 1 over 25,000. Bring the 2 out front, so we have 2 over 25,000 times Q to the first power. We want the marginal revenue when Q is equal to 10,000. So we can plug 10,000 into that variable to get a ballpark number, 10,000. So R prime of Q is equal to 2 minus 2 over 25,000 times 10,000. Plug that in your calculator, 2 minus 2 over 25 grand times 10 grand, and I believe you get 1.2, or $1.20 is the cost to produce one more item when we're producing 10,000. Revenue, number times price. Price is often a function of the number. Let's do one more problem here. Let's look at if the cost of the problem we just saw, the cost function C of Q is equal to 2100 plus 0.25Q. We're going to find the marginal profit at 15,000 items. If I can write 15,000, there we go, 15,000 items. Profit. We want the profit of Q. Hopefully you've taken some courses on how profit is calculated. Really simply, it is how much you make, your revenue, minus your cost. So we just calculated that the profit then is equal to the revenue function. Up above in gray, we found it was 2. Oops, that's the derivative. Not in gray. Up above that, the revenue was 2Q minus 1 over 2500 Q squared. That's the revenue. 2Q minus 1 over 25,000 Q squared. Minus the cost. And notice we're subtracting the entire cost function, not just the first part of the cost function. So please put it in parentheses, 2100 plus 0.25Q. So we can distribute through the parentheses. The profit is 2q minus 1 over 25,000 q squared minus 2100 minus 0.25q. We could combine like terms. I'm not going to because we're going to plug it into our calculator anyways. But we can find the derivative now of the profit formula. The derivative of 2q is just 2 minus 2 over 25,000 q. 2100 is a constant. The derivative of a constant is 0. Minus the derivative of 0.25q is 0.25. And we now have our derivative. So we want to know what's going to happen to the profit at 15,000 items. How fast is the profit changing when you've got 15,000 items? Plug that in for q to find out. P prime of 15,000 is 2 minus 2 over 25,000 times q, which is 15,000, minus 0.25. And we plug that into our calculator. And when we do, we get 0.55 or 55 cents per unit. So every unit we produce is going to increase, at this point, our profit by 55 cents. That's going to change as we get farther and farther from 15,000, but as we're close to 15,000, the profit is going to be changing at a rate of 55 cents per unit. And that is our marginal analysis. What is the cost to produce one more? Take the derivative of the cost function, of the revenue function, or of the profit function. Take a look at your homework, calculating some derivatives really quickly with these formulas. You need to know these formulas. And then second, doing some marginal analysis. Come to class with questions, and we will see you then.